Good morning. Today we are going over our Master in Chemistry homework on the mole, which I've got loaded up here. And in order to do this, I'm going to need a calculator. So I've got a calculator handy, at a periodic table, and I've got some scratch paper right here that I can kind of work through. And these are the tools that we're generally going to need to get set up and get started. Hopefully those will help us answer the questions we've got here. So starting with the first question on moles and the chemical formula, we are looking at the number of moles in a formula. So if, for instance, we have Al2 SO4 3, then this formula says that for every one molecule of Al2 SO4 3, we have 2 atoms of aluminum. That's what that little 2 means. And it looks like 3 sulfate ions, which represent 3 atoms of sulfur and 12 atoms of oxygen. All right, so this becomes now a new conversion factor. If I wanted to calculate how many atoms are in a molecule or how many moles of atoms are in a mole of molecules. Remember that 1 mole is just a batch. Like a dozen is 12 and a score is 20. A mole is a batch that consists of 6.022 times 10 to the 23rd. All right, so here we go. Calculate the number of moles of aluminum, sulfur, and oxygen atom in 5 moles of aluminum sulfate. So if I start with 5 moles of aluminum sulfate, and they want to know aluminum atoms, then I can say, all right, well, every 1 mole of aluminum sulfate contains 2 moles of aluminum atoms, because 1 molecule contains 2 atoms, 1 mole of molecules contains 2 moles of atoms. So we're just going to use this equivalency. So if I've got that, then in the end I've got 10 moles of aluminum atoms. We can do the same thing for the sulfur. Exact same story. 5 moles of aluminum sulfate. 3 moles of sulfur for every 1 mole of aluminum sulfate. It's going to give me 15 moles of sulfur. And if I do the same thing with oxygen, 5 moles of aluminum sulfate, 12 moles of oxygen for every 1 mole of aluminum sulfate. 5 times 12 is going to give me 60 moles of oxygen. So they want aluminum and then sulfur and then oxygen, comma, comma, comma. Then we have 10 aluminum, 15 of sulfur, and 60 of oxygen. Okay. All right. So same kind of story here. Let's clear our working space. Now they want the number of moles of magnesium, chlorine, and oxygen if I have 2.50 moles of magnesium perchlorate. We can pull out our conversion factors by noting that 1 mole of magnesium perchlorate is going to have 1 mole of magnesium. It's also going to have 2 moles of chlorine, and 2 times 4 gives me 8 moles of oxygen. So if I start with 2.5 moles of magnesium perchlorate, and 1 mole of magnesium for every 1 mole magnesium perchlorate, as per this equivalency, tells me I'm going to make, or I'm going to have 2.5 moles magnesium. And again, with the chlorine, now we've got 2 moles of chlorine here. For every 1 mole magnesium perchlorate. By the way, just to remind you why we're setting this up this way, it's so that those two things will cancel. Cancel, right? That's going to give me 5 moles of chlorine. And you note here also, we are including not only the measurement unit to cancel it out, but also the identity unit. The measurement and the identity are both very important. You're going to want to start including both of those things. So you have the value, the unit, and the identity, and you have to cancel these out together, because otherwise you've got moles and moles. You could be canceling out the wrong thing if you are not very careful. All right, for oxygen, last one, 2.5 moles magnesium perchlorate. And we had 8 moles of oxygen for every 1 mole of magnesium perchlorate. And 2.5 times 8 is going to be 20 moles of oxygen. You will have a calculator, you don't have to do that in your head. So that gives me 2.5 of magnesium, 5 of chlorine, and 20 of oxygen. Okay, and the last example, let's clear up our workspace. We see a sample of propane. We know that 1 propane contains 3 carbons and 8 hydrogens, right? They're asking about 16.7 moles of carbon atoms. Interesting. Okay, so they're saying we've got a sample which has 16.7 moles of carbon atoms. So instead of telling me how much of this I have, which is what we did for the parts A and B, they're telling me how much of this I have. And then instead of asking me how much of this I have or how much of that I have, they're asking me how many total moles of atoms. So we should note here that it appears that total moles of atoms, 3 plus 8, 1 mole of C3H8 has got 8 total moles of atoms. All right, so if I have 16.7 moles of just carbon, then how many total moles of atoms do I have? Are these things related? Of course, because all of the carbon came from here, and all of this contributes this many total carbon atoms. And so we can do this in 1 step or 2 step, depending on how well you can see this. If you want, you can say, look, I get 3 moles of carbon atoms for every 1 mole of C3H8. That gets me to moles of C3H8. And then you can say every 1 mole of C3H8 gets me 11 total moles of atoms. Those are going to cancel, and then that's going to give me the total number of moles of atoms. Alternatively, if you can see this, then this is extra quick. You don't have to be able to see it, but it's nice. If this is equal to this, and this is equal to this, and this is equal to this, that means that this is equal to that. So you could say for every 3 moles of carbon atoms, I've got 11 total moles of atoms. That kind of makes it a shorter, it's a shortcut. So let's plug this into our trusty calculator. 16.7 divided by 3 multiplied by 11, and I've got 61.2 total moles of atoms. Just like that. Okay, next Avogadro's number. We mentioned at the beginning 1 mole is a batch. which contains 6.022 times 10 to the 23rd of anything. Just like a dozen could be a dozen anything. You could have a score of anything. It's just a number which constitutes a particular size batch. And it's only really particularly useful at the atomic level, so that's why we don't see it elsewhere. But since 1 mole equals this, then we've got a couple different conversion factors we could use. We could have 1 mole of atoms equals this many atoms. We could have 1 mole of molecules equals this many molecules. Or if we're looking at ionic compounds which don't have distinct molecules, we could do formula units instead, but it's the same thing as the molecule. And so then we have these conversion factors that we could use. So for the first question here, they're saying, I have 5 moles of H2S. And they want to know how many molecules is that? Well, we know that 1 mole of anything is 6.022 times 10 to the 23rd of that thing. So 1 mole of H2S is that many molecules of H2S. So we can plug this in here. 5 moles of H2S. 1 mole of H2S. 6.022 times 10 to the 23rd molecules H2S, and then we can plug that into our calculator. 5 times 6.022 times 10 to the 23rd gives us, and that's just rude because I needed that in scientific notation. I don't want to count out 23 zeros. That's ridiculous. But I know that 5 times 6 is going to be 30, so this is probably 30.11 times 10 to the 23rd, or 3.01 times 10 to the 24th. Let's see, times 10 to the 24th. Hopefully your calculator will actually give you the scientific notation and not this, so you don't have to count each individual zero to figure out how far over it's going to get you. It's the downside to Windows calculator here. All right, calculate the number of moles of chlorine atoms in this many formula units of magnesium chloride. That's like saying molecules. Every time you see formula units, think molecules. It's just because ionic compounds don't make distinct molecules that they are using this fancy terminology. All right, so we're going to say 3.01 times 10 to the 24th magnesium chlorides. And they want to know how many moles of chlorine atoms. So let's go to how many moles of magnesium chloride that's going to be, because 1 mole of anything is this many of that thing. So if I have 6.022 times 10 to the 23rd of those, that would be like 1 mole of those. And then they didn't want the number of moles of magnesium chloride, they wanted the number of moles of chlorine. So you should see magnesium chloride has 2 chlorines, right? So every 1 mole magnesium chloride has 2 moles chlorine. We can plug this in. 3.01 times 10 to the 24th. Divide that by 6.022 times 10 to the 23rd. And then multiply that answer by 2. And I get 9.99667. So that's going to round up to 10.0 moles of chlorine. Right? All right. Calculate each of the following quantities in 0.180 moles of C3H520. All right. Well, let's just put some ground rules here. We know that 1 mole of C3H520 contains 6 moles of carbon. It also contains 10 moles of hydrogen, and it also contains 1 mole of oxygen. So those are going to be conversion factors we might use. And we also know Avogadro's number, 1 mole of anything equals 6.022 times 10 to the 23rd of that thing. We might use that one too. All right, so for part A, number of moles of carbon, not so bad. 0.180 moles C3H5 and I've got 6 moles of carbon for every 1 mole of my C3H5 So 0.180 times 6 gives me 1.08 moles. There we go. How many moles do I get? That's 1.08. These canceled. All right, next, 0.180 moles C3H5 And for oxygen, oh, it's 1 to 1, that's easy. 1 mole of my C3H5 gives me 1 mole of oxygen. So times 1 divided by 1, it's going to be 0.180 moles of oxygen. Okay. Oh, and now they want atoms and not just moles. So we're going to have to take this one extra step. So 0.180 moles C3H5 and we know I get 10 moles of hydrogen in that. So those cancel. And they want atoms, not moles, so 1 mole is going to be that many of anything. So 1 mole of H atoms is 6.022 times 10 to the 23rd of H atoms. And how many H atoms will that be? Times 10 divided by 1 times 6.022 times 10 to the 23rd. And again, this is 10.8396 times 10 to the 23rd. Because I'm multiplying 1.8 times 6 is going to be 10.8. So I can count all of these if I wanted to, but let's put in 10.8 times 10 to the 23rd. Nope. I think I must have got the wrong answer here. 0.180 times 10 times 6.022 to the 23rd. Oh, hello. I'm putting this into part D, but it's right here. Times 10 to the 24th. All right, always make sure you're putting that in the right text box. All right, last one. All right, now for our last question. We've still got 0.180 moles C3H5 and now they want carbon, so 6 moles of C in every 1 mole of C3H5 but they're asking for atoms, so 1 mole of C gives us 6.022 times 10 to the 23rd atoms of C. Our moles of C3H520 cancel out. Our moles of carbon cancel out. We're left with atoms of carbon, and we can plug this in here. 0.180 times 6 times 6.022 times 10 to the 23rd. And now, because I'm very smart and Googled how to do this, I'm going to click this little button, Fix to Exponent, and that converts it to scientific notation for me. I'll convert just between the long number and the short one. So this is 6.50 times 10 to the 23rd. There we go. All right, how many moles of ions are in 3.15 moles of K2SO4? For this question, we need to recognize that K2SO4 is an ionic compound, which is composed of, we've got 2 potassium ions and 1 sulfate ion. Everybody agree? Look at that for a minute. So if they want total ions, hopefully you could see what we have is 3 ions together make up the formula for K2SO4. So 1 K2SO4 has 3 ions in it. So if I have 3.15 moles K2SO4, and every 1 mole has 3 moles of ions, then I'm going to have 9.45 moles of ions. Okay, now we're going to take it up another step. This is fun. Calculating molar mass. We're looking at the periodic table, and on the periodic table you'll have a mass for every single atom on the periodic table. They call it the atomic mass, which is also known as the molar mass. That's the whole point of using a mole, is because if we define 1 mole to be 6.022 times 10 to the 23rd atoms, then the atomic mass that we see on the periodic table, for instance, we see that magnesium, 24.31, that tells us that 1 atom of magnesium weighs 24.31 atomic mass units. This is the atomic mass. That's the same as the molar mass. 1 mole of magnesium atoms weighs 24.31 grams. We call that the molar mass because that's the mass of 1 mole of that thing. So the numbers on the periodic table then do double duty. They tell us the mass of 1 atom, and they tell us the mass of 1 mole of atoms. And while the mass of 1 atom isn't particularly useful because there are no scales that measure atomic mass units, this is very useful because grams is our scientific unit for mass. So we like this a lot. This is very helpful. 1 mole of magnesium is this many grams. I can measure out that many grams. I know how many moles I've got. And because this is a fixed batch, then this will help us react whole number ratios of atoms together. All right. So if this is the atomic mass, then they want to know the molar mass of the salt. And for these, you're going to add them up. So for cadmium to chloride, I have 1 cadmium and 2 chlorines. So I just add up the mass of 1 cadmium and 2 chlorines. I'm going to write this out for the first time, and then the rest I'll just do on the calculator. So since CdCl2 has 1 cadmium plus 2 chlorines, then the mass of 1 cadmium is 112.41 grams in a mole. And then I've got 2 chlorines, and they're each 35.45 grams in a mole. So the total molar mass here plus 2 times 35.45. Gonna move that out of exponent notation. And we get a total molar mass of cadmium 2 chloride of 147.86. That's the right one. Magnesium chloride then has 1 magnesium and 2 chlorines. So magnesium is 24.31. Each chlorine, 35.45. For a total molar mass of 95.21. Our cobalt 2 chloride has 1 cobalt and 2 chlorines. So that's going to be 58.93 for the cobalt. 2 times 35.45 for the 2 chlorines. Get a total molar mass of 129.83. And finally, for beryllium chloride, we've got beryllium, which is 9.012, and 2 chlorines at 35.45, and I get 79.91 grams per mole there. Did I do that wrong? Cadmium chloride? Cadmium's 112.41 plus 2 times 35.45. Oh, I guess I put that one in wrong. Excellent. I'm glad they told me which one it was so that I could look it up. Must have done something funny on my calculator for that one. All right. Next, calculate the molar mass for manganese oxide. This looks like interesting molecule. And they didn't give me manganese or oxygen here, so we're going to have to pull up our periodic table. Got one handy, but it's kind of small, so let's zoom in here. Manganese right here is 54.94. So we have 3 times 54.94 plus oxygen up here, 16. I've got 4 times 16. And that should give me a molar mass of 228.82 grams per mole. Okay, same story here. I just add up the mass of 8 carbons plus 11 hydrogens plus 1 nitrogen plus 3 oxygens. So 8 carbons, 8 times 12.01 plus 11 hydrogens. Let's see, hydrogen is all the way over here. So 11 times 1.008 plus 1 nitrogen. All right. Nitrogen is 14.01 plus the mass of 3 oxygens, and they are each 16. That's going to give me a total of 169.178 grams in a mole. Of course, the periodic table will be given you on your exam, so you obviously do not have to memorize these numbers. You do need to be able to look it up on the periodic table and tell me what the mass of one of these is and add them up in this sort of format though. All right, so it's the same story for each of these. Calculate the molar mass. I'm going to add up the mass of 1 calcium and 1 carbon and 3 oxygen atoms. So calcium is over here, 40.08 plus 1 carbon, 12.01 plus 3 oxygens. That's 3 times 16. It's a mass of 100.09. You might get really good at memorizing some of these, not because you have to memorize them, but just because you use them a lot. And that's okay. Aluminum oxide has 2 aluminum atoms, 3 oxygen atoms. So 2 aluminums at 26.98 plus 3 oxygens at 16 gives me 101.96. don't be concerned about the significant figures feedback. We are keeping all the digits that we're getting from this particular periodic table that we're using. But depending on what periodic table you do use, you may have more or fewer digits here. So long as they say, yeah, you're there, you're fine. All right, sugar, 6 carbons, 12 hydrogens, and 6 oxygens. Ooh, 6 carbons plus 12 hydrogens. Hydrogen was over here. That's 1.008. 12 times 1.008 plus 6 oxygen atoms. Those are each 16. Gives us a total mass of 180. Okay. Right. Rubbing alcohol has 3 carbons. Using the mass of carbon here. 8 hydrogens, which is on the other side of the periodic table, but it's 1.008. And 1 oxygen at 16 gives us 60.094. All right, anesthetic, 2 nitrogens, 1 oxygen. Okay, 2 times 14.01 plus 16 gives me a mass of 44.02. And finally, potassium cyanide. Potassium's back over here, the mass of 39.1 plus carbon, 12.01 plus a nitrogen at 14.01. I get a total mass of 65.12. All right, and now multiple choice question, same kind of thing. Formula weight of copper 2 chloride is how many grams? Ooh, this one is extra tricky because they didn't give you the formula, they gave you the name. So you have to remember how to name compounds in order to get the right formula so you can add up the right mass. That's an important part of this. So you have to remember copper 2 chloride. All right, this is a ionic compound between copper 2 and chloride. And you know that the chloride ion has a charge of -1 because it's in group 7. And you know that the copper 2 ion has a charge of +2 because they told you that it had a charge of 2. Therefore, when I put this together to make my new compound, it's going to have 1 copper for every 2 chlorine ions in order for those charges to balance. So CuCl2 is the right formula for copper chloride, and that's what we need in order to correctly answer this question. All right, so 2 chlorines, that's easy. 2 times 35.45, and 1 copper, here we go, it's 63.55, gives us a total mass of 134.45. Okay, don't forget how to name things and put ionic compounds together. You're going to have to continue to do that throughout the semester. All right, so what's the point of this molar mass? That was pretty easy, which made it fun. But what am I going to do with that and why? Well, the next step we're going to do is use that as a conversion factor between moles and grams. So when I say that something, say, is 58.5 grams per mole, then that's just the same as saying that 1 mole is 58.5 grams, or that if I have 58.5 grams of that thing, I've got 1 mole of that thing. Specifically, this is sodium chloride. So remember, we are including both the measurement unit and the identity unit along with mathematical value that we're given. So 1 mole of sodium chloride equals 58.5 grams of sodium chloride. So if I give you the number of moles, you could use this to convert to grams, or if I give you the number of grams, you could use that to convert to moles. That's what we're going to be doing here. So starting with this one, I have 8.70 moles of magnesium chloride. They want to know how much does that weigh in grams. Note units here, grams. So we're going to use our periodic table to first calculate the number of grams in a mole for magnesium chloride. So we look at this and we say, all right, MgCl2 has 2 chlorines and 1 magnesium. It's all the way back here, 24.31, 24.31. So we have a molar mass for magnesium chloride of 95.21 grams per mole. So that tells us that 1 mole magnesium chloride weighs 95.21 grams. So now I can apply that to the original 8.70 moles that I got. I'm going to put this on the bottom so that will cancel. And this on the top. When I apply that, 95.21, multiply that by 8.70 moles, I get a total mass of 828.32 grams. Okay. They set it up here for you as well. All right, same story. How many moles of nitrogen are in this many grams of nitrous oxide? So for this one, since we're looking at N2O, we need to look up on the periodic table. Scroll over. N2O has 2 nitrogens and 1 oxygen. So we have 44.02 grams of N2O in 1 mole. So if I start with 70 grams, and they want to know how many moles, I'm going to set this up with grams on the bottom, so that will cancel, and moles on the top, so that will be what we are left with. Grams cancel. Plug this in, divided by 44.02. 1.59 moles of N2O. All right, when in doubt, reread the question more carefully. How many moles of nitrogen are in 70 grams of nitrous oxide? Ah, they're asking for moles of nitrogen, not moles of N2O. I did not go far enough. So, let's take that one step further. We can see hopefully that 1 mole of N2O contains 2 nitrogens. 2 moles of nitrogen. There we go. Just didn't read the problem carefully enough. You ever done that? 70 divided by 44.02 multiplied by 2 gives me 3.18 moles of nitrogen. All right, so that's it for question 8. Okay, how many moles are contained in each of the following? They give us grams, so we'll need to look up the periodic table, the molar mass, and convert from grams to moles for each of these. So, 27 grams of calcium. Periodic table tells us that calcium is 40.08 grams in a mole. Plug that in. .634. Okay, read that more clearly. 0.674. I don't know where that 3 came from. Here we go. Always make sure that you're reporting what it is that your calculator is actually telling you. Okay, same story for sulfur. We start with 4.60 grams of sulfur. Look at our periodic table. We see that sulfur has a mass of 32.07 grams per mole. Set it up this way so our grams of sulfur will cancel. We're left with moles of sulfur, which is what they asked us for. Oh. Start over. Gives us 0.143 moles. All right, next we're looking at H2O. So we've got 1 oxygen and 2 hydrogens. 1 oxygen is 16. 2 hydrogens, periodic table says they are 1.008. So we have 18.016 grams per mole. So if I start with 40 grams of water, and this is 18.016 grams per mole. We want grams on the bottom. Grams of H2O cancel. We get 2.22 moles. And finally, 14.9 grams of oxygen. Note these are O2, so I've got 2 oxygen atoms in a molecule of oxygen. Each atom weighs 16. So 16 times 2 gives us 32 grams per mole for oxygen. So 14.9 grams of oxygen, 32 grams of oxygen, and 1 mole of oxygen. Grams of oxygen cancels. 14.9 divided by 32 gives us 0.466 moles. All right, going the other direction, if I'm given moles, determining how many grams I have, it's the exact same process, but then I'm going to reverse which direction I do this. So if, for instance, let's clean up some space here. I have 2.3 moles potassium. I look on the periodic table and I determine that potassium has a mass of 39.10 grams per mole. That tells me I need to put the moles on the bottom, so they'll cancel. I can plug this in. Should get 89.9 grams of potassium. So what you'll notice is that when you're converting from grams to moles, you're going to divide by the molar mass. When you're converting from moles to grams, you're going to multiply by the molar mass. But I don't want you to memorize those as a rule of thumb because it's very easy to get those mixed up. What I want you to do is to sit down and write out your dimensional analysis, because the dimensional analysis will tell you which one you need to do in order to cancel out your units appropriately. And then you don't have to guess or wonder what it is you should be doing, because dimensional analysis tells you what you need to be doing. 2.7 moles of carbon, carbon is 12.01 grams per mole. So 2.7 times 12.01 gives us 32.4 grams. Okay. Next, phosphorus. 0.3 moles of phosphorus. Periodic table is 30.097 grams per mole. Get 9.03 grams. And finally, 13.5 moles of helium. Periodic table says helium is 4.003 grams per mole. Moles of He cancel. Get 54.0 grams. All right, last question. We're looking at lovastatin, drug used to lower serum cholesterol. Has this formula. First, calculate the molar mass. Right, that's a lot of atoms, but I can do that. It's 24 carbons, and they each weigh 12.01. And 36 hydrogens, and they each weigh 1.008. Add 5 oxygen atoms, they each weigh 16. So 5 times 16. I get a total molar mass of 404.528 grams per mole. I'm going to say grams. Should be grams per mole, but they are saying the molar mass, so that's the mass of 1 mole would be that many grams. Unless they really want me to do grams per mole. Yes, okay. So they just wanted those units there. 404.53 grams per mole. And how many moles of lovastatin are present in a typical dose of one 10 milligram tablet? Ooh, excellent. So we're doing mole to gram conversion, but we're not looking at grams. They gave us milligrams. So we have to remember our metric prefixes. So if we start here with 10 milligrams of lovastatin. And we've got grams per mole, not milligrams. So we have to remember 1 milligram is 1 times 10 to the negative 3 grams. So 1 milligram of anything, including lovastatin, 1 times 10 to the negative 3 grams lovastatin. Now we've got grams and moles. We want grams on bottom, so that'll cancel. 404 grams of lovastatin in 1 mole of lovastatin. And our grams will cancel. Now we'll have units of moles of lovastatin. So 10 milligrams multiplied by 1 times 10 to the negative 3 grams in a milligram divided by 404 grams in a mole gives us 2.475 times 10 to the minus 5th moles of lovastatin. So we're going to say 2.48, or I think probably 2.5, since we've only got 1 or 2 significant digits here, and that's going to be moles. Oh, I'm sorry, 2.5 times 10 to the minus 5th, of course. Forgot that part. Right, that is it. I hope that was helpful, and I hope you have a great day.